Problem 3. Two radio antennas radiating in phase are located at points A and B 200 meters apart. The radio waves have a frequency of 5.8 times 10 to the 6 Hz. A. At what distance from B will there be the first destructive interference location along the BC line? B. What is the relative intensity at the point x equals to 100 meters from point B? I. If this point is closer to a dark or bright fringe, what is the fringe number? If not, is it closer to a dark or bright fringe? Draw a sketch of the interference pattern and show where this location x is located. First step is to determine the interference pattern by calculating the interference parameter, d over lambda. The wavelength of the radio antenna is given by c equals lambda times frequency. So lambda, when you plug in the speed of light, gives you 51.7 meters. Then the diffraction parameter d over lambda is in 3.87 to 3 sig figs. In the path difference equation, delta r is d sine theta, which is equal to mc lambda. My mc maximum value is the diffraction parameter, which is 3.87. What does this value mean? mc equals to 0 implies that the path difference must be 0. The only way this could be true is if you're at infinity. If mc is equal to 3, that means that there are 3 bright fringes. That is mc1, mc2, mc3. But when I look at 3.87, this m value of 0.87, I know that m equal to a half integer is related to a dark fringe, where any whole integer is a bright fringe. So you could see here that 0.87 is going to be closer to a bright fringe than it is a dark fringe. And what you're seeing here is that it's not at maximum intensity. So it's closer to a bright fringe than a dark fringe. Sketching the interference pattern, at mc equal to 0, we know that's at infinity. Then I got 3 brights, full brights. So I get 1, 2, 3, and then I got mc equals to 387, but that's not at all the way up. So then if I look at md, then I could see that that's got to be 0, 1, 2, 3. So if I look at the number of dark fringes, turns out that I see 4 of them. How many brights do I see? I see 1, 2, 3, 4, and then I get a partial max. I'm going to get 4 maximal bright fringes, 0, which is 1, 2, 3, 4. I get 1 partial bright fringe, which is at 3.87, and I get 4 dark fringes, 1, 2, 3, 4. What location will the first dark fringe appear from source B? We could see here that it's got to be MD equal to 3. Picture-wise, I have A, B, and C. A travels farther than B by the path difference delta R. So if I want to calculate what that value is, I know that this occurs at MD equals to 3, so then I write MD equal to 3. I know that this angle here must be theta of 3. So now I have a full triangle. I can calculate the angle using this relationship, and if I know the side D, I can then calculate this length along the BC line. Once again, I calculate theta 3 from the path difference equation. Once I have that, I then solve the triangle for x3. I know what D is, I know what theta 3 is, so now I can solve for x3, the distance that's to the first minima from source B. Path difference equation gives dr equal to d sine theta 3, which is equal to 3, md equal to 3 plus 1/2 times lambda. Solving for theta 3, I then get that I get the sine inverse of 3.5 divided by the diffraction parameter at an angle of 64.7 degrees. From the triangle, I get that d divided by x3 equals the tan of theta 3. So x3 is equal to d divided by tan theta 3, which then gives me a value of 94.5 meters. So this is how far minima MD equal to 3 is located. Problem 4. In a single slit diffraction experiment, let the wavelength of the light be 500 nanometers, the slit width is 6 microns, and the viewing screen be a distance 3 meters. A. How many minimas and maximas does this diffraction pattern have? Sketch the diffraction pattern in detail. B. At what distance does the dark fringe that is most distant from the center occur? C. What is the approximate location and relative intensity of the third diffraction maxima? Sketching out the situation, I have incoming light, which has a wavelength of 500 nanometers. So instead of writing 500 nanometers, I'm going to convert that into microns. So 500 nanometers is 0.5 microns. I have a slit width opening of 6 microns, and the screen distance is 3 meters. A. To understand what the diffraction pattern looks like, we have to calculate the diffraction parameter. And this is A over lambda, which is 6 microns divided by 0.5, which gives me 12. And therefore, the maximum number of minimas is given by the path difference equation, but for the maximum, sine of theta is 1, so then the maximum number of ND then is the diffraction parameter, which is 12. That means that there are exactly 12 minimas. Total number of minimas and maximas is that the total minimas is 2 times ND, which will give you 24. The total maximas is 1 plus 2 times ND minus 1, which gives you 23. The diffraction pattern then looks like this. I'm going to have 12 minimas. In other words, look at that ND is going to be all the way up to 12. And if I look at the phase alpha, it's 0, pi, 2 pi, 3 pi, 4 pi, all the way to 12 pi. And then the pattern ends there. To determine the screen distance of the most distant minima, that is ND equal to 12, we set up the triangle. So here's my situation where from the slit opening to the screen is D. The distance that I want to calculate is delta y12, where I have this angle theta 1, 2 here. However, I know that all the minimas have the same spacings between them. So I can also write delta y12 is equal to 12 times the spacing of one of the minimas, the first minima. So if I calculate this distance, then I know that I'm going to have, I could then multiply that by 12 to get that distance. The path difference equation, I have A sine 1 is equal to 1 times lambda. Now, if I solve for theta 1, I get theta 1 is going to be the sine inverse of 1 over the diffraction parameter, which gives me 4.78 degrees. From this above triangle, I get delta y1 is going to be d tan of theta 1, which will then be 3 times the tan of 4.78 degrees, so I get 0.251 meters. The distance from the central maxima to ND equals to 12 is then delta y12 equals 12 delta y1, which then is 3 meters. The location of the third maxima can be estimated from the diffraction pattern. We know that the separations between minimas is exact. However, there is a small error for the location of the third maxima. It is not in the middle between 3 and 4. So it's approximately 3.5, but there's less than 1% there. So I can write this delta y NC equal to 3.5 then is going to be approximately equal to 3.5 times the separation between the minimas. Plugging in delta y1, I get that this location is 87.8 centimeters. Phase location alpha of the secondary maximas is given by the path difference equation. So in other words, if I have alpha, it's pi a sine theta divided by lambda, but for maximas, it's approximately equal to what? NC plus 1/2 times lambda. So substituting that in, that alpha is approximately NC plus 1/2 times pi. In other words, it's 3/2 pi, 5/2 pi, 7/2 pi. Since this is the third maxima, that's the phase location. Relative intensity at 7 pi over 2 is then going to be sine of alpha over alpha squared. So if I have sine squared of 7 pi over 2, that's got to be 1. So then I have, it's going to be 0.00827 or 0.827% for the relative intensity.